2 was actually accurate. And so, yes, negative 4 comma 2 lies on Spidey's path. Okay, so we've got our point, and we now need to calculate our slope. Now, when I look at this equation, which describes our curve over here, I'm going to be very hard-pressed to solve for y. Okay. There's a y in a couple of places. There's also a y squared. And so this is going to be very challenging to try and solve this equation for y. So we're going to go straight to our implicit differentiation method of finding dy dx. So what I'll do is I'll start by writing out the equation. But what I'm thinking of is that everywhere in this equation that I see a y, I'm thinking of y as a function of x. So notice that this purple curve does not pass the vertical line test, but in a small neighborhood around the point that I'm interested in, this curve does pass the vertical line test. So we're going to think of y as a function of x. So we've got 4 times f of x squared plus 4x times f of x plus 40 times f of x, which is equal to 400 plus 80x minus x squared. Alright, so we've now taken every y and replaced it with an f of x. We're thinking of y as a function of x. And now I'm going to take this entire equation and I'm going to differentiate both sides with respect to x. So take the derivative with respect to x on both sides of our equation. So on the left side, I have a couple of terms that are all combined through addition, and so I can think of each of those terms as separate terms and take their derivatives separately. My first one is 4 times f of x squared. When I take this derivative, that 4 I can carry along because it's a constant multiplied by something changing. And then I'm going to use the chain rule because I have a fancy thing. I have f of x, that entire expression, squared. So my chain rule says, okay, I'm carrying along that 4. Chain rule says take the derivative of the outside, keeping the inside the same. So I've got 2 times f of x raised to the first power, derivative of the outside, keeping the inside the same, times the derivative of the inside. And my inside function was f of x, so its derivative is f prime. That is, thank you, 4 times 2. Okay. So that's our derivative of the first term. Any questions about that one? Our next term is 4x times f of x. And so what I see there is I've got 4x times f of x. So when I do my derivative here, I've got a product rule to deal with. Okay? I've got 4x multiplied by f of x. So my derivative for my product rule says first times the derivative of the second, so our first is 4x, times derivative of the second, derivative of f of x is f prime. So first times derivative of the second, plus second, f of x, times derivative of the first. So derivative of 4x is 4. Are there any questions about this middle term, the purple term? Product rule. First times derivative of the second plus second times derivative of the first. Okay, so now I'll go into my next term, the 40 times f of x. And so here we have a constant times something that's changing, so I can carry along that constant, the 40, and take the derivative of the f of x, and so its derivative is f prime of x. And now we're up to our equals sign. On the right side, things are easier for us. There is no f of x at all on the right side over here, so we can take our derivatives without thinking too hard. Derivative of 400 is 0. Derivative of 80 times x is 80. And the derivative of x squared is 2x, so I have 80 minus 2x on the right side. Okay, so we've now implicitly differentiated our equation. Are there any questions about that?
What rule was the third one?
This one right here?
Yeah,
So this was our 40 times f of x.
right.
And so, because it's a constant times something that's changing, I carry along the constant, and then take the derivative of f of x.
Yeah, I know how. I was just wondering what the rule was. Is that a rule? What's
So the one there's a rule that says that
what rule it was?
y is equal to c times f of x, then dy dx is equal to c times the derivative of f of x.
Okay.
That it said that it says that we can pull a constant in front of the derivative sign.
Yeah, I guess that's rule 5.
I don't remember the number, but it could have been.
That's what I was looking for, but I think I got it.
Just a question. So does that mean that the derivatives are equal to each other?
That this derivative over here
Yeah.
is equal to this derivative. It says that for this particular curve, it says that this relationship is equal to, yeah, well, yeah, so the derivative of this expression is equal to the derivative of this expression. It doesn't mean that, yes, absolutely that is a yes. So yes, so the derivative of, because the two original expressions are equal to each other, then their derivatives are also equal to each other.
So if two equations are equal to each other, their derivatives are the same even though they're different equations.
So these are not two equations equal to each other. These are two expressions that are equal to each other.
Well, there's the same equation written two different ways then.
The word equation means you have an equal sign in there. So basically what I'm doing is I'm picking on semantics right now. So the word equation indicates that you have a left and a right side and an equal sign in between.
There is this right side.
Right, but it's one equation, two expressions that are equal to each other. Does that make sense?
Yeah.
Sure. Okay.
Sure.
Is there another way to say that? If you graphed both of those, they would look the same?
Well, if we were to, it wouldn't really make sense for us to graph, I mean, I could graph this one because it's all just in terms of x's, and I could say y equals this, but that would be the graph of a function y is equal to this stuff. And we're actually saying that this whole thing over here is equal to this whole piece. And so really what we're saying is that we are looking for the set of all ordered pairs x comma y that actually work to plug into both sides of this equation and give us a valid equation. And those set of points are exactly the points along this curve right here.
So you want to be able to just take that 80 minus 2x and stick it in on the other side then?
What would you want to stick it in for? Yeah. This 80 minus 2x is equal to that whole left-hand side.
Yeah.
It's not equal to a piece of it. It's equal to the whole thing. So if you ever saw this jump out at you on a dark alley, this entire left-hand side, you could say, I'm not looking at you, I'm going to replace you with this. But that's really about the best you can do. And this is only true for points that satisfy, or the curve, it's only true for along this curve right here. So if you plug in x equals 0, 0, not along the curve, so that relation on the derivatives doesn't count anymore. So it's only valid along this curve. Okay. All right, these are good questions, and they're tricky questions, so I'm hoping I'm kind of answering it the way that you're thinking about. Okay, so we've taken our derivative. We've looked at the left side of the equation, the right side of the equation, and what I see in here is that I see f primes all over the place. And remember that my goal is to calculate or to find dy over dx, or also equivalently f prime of x. So I've got to solve that equation for f prime of x. To make my life easier, this is a lot of parentheses, and so dealing with parentheses is kind of a pain in the neck. I'm going to revert back to my x's and y notation. So I've got 4 times 2, which is 8, times y times dy over dx, plus 4 times x times dy over dx, plus 4 times y, plus 40 times dy over dx. And all of that is equal to 80 minus 2x. And so we would like to solve this equation for dy dx. All right, and what you'll notice, Ben, your question?
Oh, no.
Okay. So what you'll notice is that there are dy dx's in several places, but no matter where it shows up, it only shows up once. Like it's not squared or raised to the 3rd power or anything like that. So this equation is actually linear in terms of dy dx. And so in order to solve this, what we want to do is group all the terms that involve dy dx on one side, and anything that does not involve dy dx, we want to move over to the other side. So in this case, we're going to be subtracting off 4y. All right, so we now have 8y times dy over dx plus 4x times dy over dx plus 40 times dy over dx is equal to 80 minus 2x minus 4y. All right, so everything involving a dy dx is on the left side, everything not involving a dy dx is on the right side. And so what that means is that now we can factor out a dy over dx. And so we've got dy over dx times the quantity 8y plus 4x plus 40. And all of that is equal to 80 minus 2x minus 4y. All right. We still are solving for dy over dx. What's our next step?
Divide everything on the left to the right.
Yeah, everything over here on the left side, we're going to divide by on both sides, and we're going to be left with dy over dx is equal to 80 minus 2x minus 4y all over 8y plus 4x plus 40. And so what we've just come up with right here is that we've come up with a description of the slope of the tangent line to Spidey's path at any xy ordered pair point that lies on his path. Now, I've semi-lied to you, so I'm going to put a little star on the word any.
It's just for our neighborhood, right?
Just for our neighborhood. So as long as we can draw a neighborhood around our point where everywhere in that neighborhood we pass the vertical, our curve passes the vertical line test, then this is valid. So for example, on this particular picture, there is a place where the curve has a vertical tangent, and that point is roughly this point right here. And so whatever that point is, I could not plug in this ordered xy pair into this expression and come up with a slope, mainly because the slope that I would get would have a 0 in the denominator. Okay. And so, but other than that point, the place where we have a vertical tangent, any other point on this curve, the slope can be described by this expression. Any other point on this curve, you can draw a neighborhood around that point, and we have a function. All right, so are there any questions on that expression? Yes.
So, wouldn't the math still be the same if the point was somewhere else on the curve?
Yes, so if you found another point on the curve up here, and you know what that ordered pair is, you could plug that ordered pair into here as well.
So, what did you just say about it wouldn't work unless it's in the neighborhood?
So it wouldn't work it would work for this point out here because I can draw a little neighborhood around that point, and the purple curve passes the vertical line test. But it would not work for this point right here, and I'm going to blow up this point here. That point is this place right here where I have a vertical tangent, and any kind of a neighborhood, no matter how tiny I make that neighborhood, this is still not going to pass the vertical line test. So it's not going to work for this point right there. But any other point, and even this point right here, I can make my neighborhood small enough that it still passes the vertical line test within that neighborhood.
Basically, set the denominator equal to 0.
Yes, so this point here is where if you did plug in that point, you get a denominator of 0.
So it also go back to the idea that any vertical point is not differentiable.
That's correct. Yes.
So would that work as you go negative on that curve?
On this curve here. So if we were to mean like down here before his existence, it would work here because I can draw a little circle around there and my path passes the vertical line test. So, yep, I can draw my tangent and I can plug in that point, as long as I know that ordered pair, which is not necessarily easy to find. This is a nice, easy point. The rest of these could be very funky values, and that could be a problem.
I don't want to do that on the test. But
Right, right.
thank you.
So this is actually a really cool tool. Okay, it allows us to come up with slopes for curves that are extremely crazy types of curves. All right, so we're not quite done with the problem, though. This is our slope of the tangent to Spidey's path at any xy that lies on his path. And the asterisk is that as long as we can draw a neighborhood around the point where the curve passes the vertical line test within the neighborhood.
Just out of curiosity, if they did want you to figure out what it was at the point where it's vertical, how would you end up doing it? Because there is an answer for it, right?
Well, so our slope would be vertical, right?
Yeah.
Which would indicate very likely that this denominator would be equal to 0.
Yeah.
And so, so if we, wait, so are you asking if we would find that point, or what we would do about finding the slope at that point?
Well, what would we do to find that, like, it just means the slope is vertical, it doesn't affect the equation with the y minus y1 equals 1 over 0 or whatever you want to put.
Well, if I want to draw a vertical line, then I can't write my vertical line as y equals mx plus b. I have to write it as x equals whatever that x value is.
Okay.
So that's how I would draw that tangent line and write its equation.
Okay.
Okay, so let's wrap up this question. Okay, so our big question was find the equation of the tangent line to the point where Spidey gets cut off from his original path. And so right now, we have a point, and that point was -4, 2. And we have a slope, which is given by dy over dx. And so what we're going to need to do is to plug in our point, -4, 2, into our formula for dy dx. All right, so at 4, -2.
Oh wait, -4, 2.
Oh, I'm sorry, thank you. -4, 2. dy over dx looks like 80 minus 2 times x, which is -4, minus 4 times y, which is 2, over 8 times y, which is 2, plus 4 times x, which is -4, plus 40. All right. Has anybody gone ahead and calculated this value?
2 over 40.
What did you come up with?
80 over 40.
80 over 40. Y over dx. 80 over 40, which gives us 2. Do I have a second or a third on that value?
Yep.
So, okay, great. So our slope is 2. So now we've got a slope. We've got a point. We can write down the equation of our tangent line. So the equation of our tangent line looks like y minus y1 is equal to slope times x minus x1. So in our case, we've got y minus 2 is equal to slope, which is also 2, times x plus 4. All right, so we can simplify this thing, and so we've got 2x plus 8 is equal to y minus 2. We'll add 2 to both sides. And our final conclusion is that y is equal to 2x plus 10. And we can now go back to our boss, Walt, and tell Walt that the equation of this tangent line, the path that Spider-Man should follow once his web is cut, is y is equal to 2x plus 10. And now they can go on with their animation. All right, are there any questions about what we've done here? All right, so thank you for listening. I think